Hey guys, James here. Today I'd like to talk to you about dealing with outliers in your statistical models. I'm making this video because I've seen a few posts in recent that suggest there is some confusion about how we should approach outliers. While confusion is okay, I've seen some other posts that suggest really absurd things, like just add more variables to the model until those outliers aren't outliers. I own more stats textbooks than I would like to actually admit in a public addressment such as this, but I'm pretty sure in every one of them it says not to do that. Later in this video, I will talk about an advanced method that permits you to leave outliers in your model while ensuring they don't influence it to any extremes. But first I'd like to start by talking about deleting outliers, which has a lot of controversy surrounding it. Some people think deleting outliers is cool, others think only normies delete outliers, and you may find a lot of blood being spilled on the internet regarding this topic. I want to stress that deleting outliers is wholesomely controversial, and what actually should be done with them is highly dependent on the subject your data pertains to. However, I will say that deleting outliers from your data modeling can be acceptable, but you should never delete them from your overall research. In other words, you build your statistical models without your outliers, but you should always comment on them in any report or article that you are writing. This doesn't mean just merely stating, we deleted outliers, but provide some actual details about how you spotted them, whether it was highly technical or just with an eye test, and maybe even some details about them. For example, you could say something like, this 6-foot-tall 4-year-old was really damn strange, and we only care about normal 4-year-olds, so we did not include them in our inferential model. But guys, we actually found a 6-foot-tall 4-year-old. Do we get a prize? I would put that in a publication. It provides other readers with enough information to understand the nature of the outlier, and I think we'd all be happier if the 6-foot-tall 4-year-old was being excluded from medical research that was aimed to be highly generalizable. Now, what if you don't want to delete outliers? Well, that's reasonable too. To do this, you can use one of many different robust regression procedures. These approaches build a regression model where the impact of outliers is dampened, fitting a model that is appropriate for the majority of cases rather than all cases. There are a few different robust regression methods, but I'm going to describe one that I have particular experience with called iteratively reweighted least squares. This procedure assigns a weight to each data point, determining how much influence that point will have on the model being fit. This weight is roughly determined by how far the point falls from an initially built ordinary least squares regression model. Once we fit a weighted model to our data, we will get new weights from that model and build a new model, and we'll perform this process over and over and over again until the model remains relatively the same each time we reassemble it. When this happens, we usually say the model has converged. Now, it's important to remember that every time we build a new iteration, we are recalculating the weights for our data points. As this outlier up here gets farther and farther away from the model, its weight gets smaller, meaning its influence decreases. In the meantime, these guys down here are getting closer and closer to the model, so their weights are increasing and their influence is being amplified. So, as distance from the model increases, influence decreases, and as distance from the model decreases, influence increases. Now, there is something I left out that needs to be talked about. If we were to just delete these outliers and fit an ordinary regression model, we would get the same result. This is because this outlier was so far away that it received a super small weight and became irrelevant. So doing this is essentially the same as deleting outliers, but you are using a more computationally heavy procedure for selecting what data points are up for deletion. Additionally, it gives them at least a few chances to leave their mark on the model. Now, this doesn't always have to be the case. You can customize the iterative weighting procedure to ensure that no points get deleted. I hope you really care about this topic because we're about to really dive into it. This is done by choosing a weight function that determines how your data points get weighted each time the model is reassembled. You can pick a highly conservative weight function that assigns a weight of 0 to any outlying data points, which is the same as deleting them from your model, or you can use a very liberal weight function that will never assign a weight of 0, ensuring that all data points have some influence on your model. Here are some examples of these weight functions. This conservative one here will delete outliers, whereas this liberal one will dampen their influence but never fully delete them. We can see that the y-axis represents the weight we assign to a data point, and the x-axis represents the scaled residual pertaining to that data point, being a measurement of how far it falls from our model. So, for example, if we have a point that is 3 standardized units distance from our model, we would look up this value on the x-axis and say, oh, okay, we're going to assign it this weight here. And we can see that the conservative weight function assigns a lower weight than the liberal weight function. Interestingly, this first weight function, as we can see, treats any point that does not fit the model perfectly as needing dampening, and thus takes a very conservative approach to building iterative models. Notice that after a certain degree of distance, this function will assign a weight of 0, essentially deleting the point from the model entirely. This second weight function takes a very different approach. Notice that the top of the function is flat, so points that don't conform perfectly to the model will still receive a weight of 1 and have full influence on the model. Additionally, the trails of the weight function never pass below a given threshold, and thus will always assign a weight that is equal to or greater than that threshold, regardless of the point's distance from the model. These functions are referred to as the bi-square and uber weight functions, respectively. They are likely the most commonly used weight functions when using iterative reweighted least squares. Now, to make things more interesting, you can select different weight functions for different iterations of your model building process. For instance, it's beneficial to use the uber weight function for the first iteration of your procedure, and then use the bi-square function in all following iterations. This ensures that the first iteration does not cut out too many data points without giving them a chance to be part of the model. The bi-square weight function's conservative nature can sometimes ignore too many data points and heavily bias your results. That being said, there are many different weight functions and ways for you to initialize your model building process. Covering these is a bit beyond the scope of this video, but if you're interested, I encourage you to do a literature search on the topic. As a last example of interest, I've assembled some models side by side that only use either the bi-square weight function or the uber weight function. As we can see, the bi-square weight function essentially deletes our outliers from the model, while the uber weight function only dampens its influence. Now, something else that should be mentioned is that when it comes to outliers, there's no one perfect way to approach them. The reality is that an outlier is an outlier and will always be problematic when performing data analysis. Generally, we perform statistics to try and explain things, and by definition, an outlier is something we just can't explain. The method I've given you in this video is a good method for approaching outliers because it aims to fit a good statistical model while treating anomalies with caution. However, there are many other approaches out there that are just as good, or just as bad I should say, because outliers are very hard to deal with if you truly have no insight into their nature. I hope you've enjoyed this video, and thanks for watching.